students, this is Kamal Sarma. Welcome to my class. Today I am going to discuss about concept of elastic analysis. Most of the structural analysis or theories we are going to discuss or discussing right now is on the elastic analysis. Okay, there are two kinds of analysis. One is the elastic, another is plastic. To understand it fully, I am showing you something. This is a rubber band. So if I pull it, it's stressed. When I release my force or pull, it comes back to original. This is the property of elasticity. That means as soon as I release my force, it comes back to original position. When I put my force there, the rubber band is expanded. This is called elastic property. The plastic property is that when you pull something or when you distort something, it doesn't come back to original position. That is plastic. Let me have a plastic strip. When I pull it, it's stressed. You see, it's stressed. It is elongated. It doesn't come back to original position. This is called plastic. It's a plastic. You see, it's going stressed, but when I release the force, it has got a deformed shape. It is elongated but doesn't come back to original position. This is called plastic. Okay, steel, that is the material we use for structural engineering or structural purpose, is very elastic. You'll be surprised, steel is more elastic than rubber. Okay, let us draw the stress strain curve of the mild steel as well as the high carbon steel. Okay, this side x-axis is your strain and y-axis is your stress. You know, stress is force divided by area for direct tension. Force P divided by A is your stress. A strain is, if you have a small length, this is deformation, the original length divided by original length is your strain. Suppose you have a rod like this, okay? It has got a cross-sectional area like a square, or this is a circular, and the area, you know the area there, okay? So this is the area of this cross section, and this is the length L, and when you apply a force P, suppose it is fixed there, then what happens? It is elongated a little bit. This is your delta L. So delta L divided by original length is your strain, and the force divided by cross-sectional area is your stress for an ordinary case. Okay, for a axially forced member. Okay, so now if you have a steel rod, mild steel say, if you are pulling, then it will be elongated. The amount of stress and strain is proportional to certain extent. This is called Hooke's law. What is Hooke's law says? Stress, if you call sigma is the stress, this is called sigma, and strain you can say, it is say delta. Okay, sigma is proportional to strain. and or you can write it like this: sigma equal to K times of delta. This is the K is the constant of proportionality, and for directly axial member, or we call K as E. So E is modulus of elasticity. Is equal to stress divided by strain. This is called E. And this follows Hooke's law. Now if you draw the every instant of the elongation and the P by A, it will be curved like this. Stress is proportional to strain to certain extent. Suppose up to this point, this is the limit of proportionality. Okay, the limit of proportionality up to that point. After that, the materials try to yield a little bit, and after that it comes down like that, a little bit of horizontal, then it increases. This is the maximum you get. So this is the F of U ultimate, and at this point we have got a yield stress Fy. F is stress. Actually, you can say, instead of sigma, we can say this F, stress. So that means if sigma is delta, strain is delta. Okay? So your, up to this point, limit of proportionality, stress is proportional to strain. So that means E equal to strain divided by stress divided by strain. So this follows the Hooke's law. And what is Fy? Fy is the yield stress, at which point it is assumed the structure started going to yield. That means it is giving away, and from here the plastic range starts. So this part is plastic plateau. Is a plateau. After that, this part is strain hardening, and after that it goes down and neck is formed at this point, and here it collapses, it breaks down. Okay, so this is the stress strain curve for a mild steel. But how can you find an Fy? Okay, so Fy, there is an easy way of getting a Fy. But one thing before I should say, when you have got the curve like this, at any point you release the force, just like a rubber band, it will come back to zero, original position. That is the elasticity. When you, from a steel member, when you take out the force P, it will come back to zero elongation, zero stress. So at this point, if you draw a vertical line, this shaded area is the strain energy. It saves the energy, as well as when the force is taken out, it releases the energy. Okay, so this is the energy, strain energy. Okay, now what happens? This is the E. I told you E, right? E, modulus of elasticity is the slope of this tangent of the theta. slope. Tangent of theta E equal to, this is the angle theta, equal to tan theta. This, which is equal to nothing but F divided by strain. You see? Now, it is true only to the proportionality limit here. After that, it starts to yield. Now, the yield is actually a yield stress is measured if you, at this point, suppose at this point, anywhere in the plastic range, this is called plastic range. At any point you release the force, it follows the original curve. It's similar, parallel to it. It makes a line parallel, but there is a residual force, residual stress. I'm sorry, residual strain. This one is residual strain. So, if this value is 0.2% or 0.002, and that point, this is your yield stress. In industry, it is called, also called, it is, we call it yield stress. In industry, it is also called as proof stress. Proof stress is the 0.002 strain, whatever the stress is, that is called proof stress. Sometimes some people consider it as 0.001 also, but normally it is 0.002 is the yield stress or proof stress. Proof stress sometimes it is called 0.001, but that doesn't matter. Usually it is 0.002 is usually people takes it because it is equal to the yield stress. In a high carbon steel, that is a high strength steel, it follows the similar curve to certain extent, but it is something like this. It reaches the FU at a lower distance from this curve, but it is that means the structure is less ductile. But there also it is the 0.001 at this point, 0.002, sorry, strain. It is 0.002 strain for here also. So this is the Fy yield stress for this curve. So all our design, we are careful not to exceed Fy yield stress. That is our goal. Okay? Why I say that is the goal? Remember last time we discussed something. We have two equations, right? We say Rm, it is the nominal capacity of a section, nominal strength, design strength of the section, initial design section, and if it is in working stress design is divided by factor of safety omega, which is greater than equal to I equal to 1 to I Q and I. This is the equation. This is the design required for different loading. That is the reason you have the summation. For dead load, design required for the dead load, live load, or etc. This side, this Fy doesn't influence, but this side it is influenced because Rm is a function of Fy. Rm is a function of Fy, that's the yield stress. I told you, this is for the working stress. This is the working stress formula. For limit state, we have a formula like that. Remember that? And F of Y, the function of yield stress, equal to, what is our equation? Gamma I summation of gamma I Q and I and I equal to 1 to I. I is the total number of load combination. I is nothing but the total number of load combination. Sometimes it is 3, sometimes 4. Say live load, dead load, snow load, wind load, all these different load conditions. So I is the total number you have in that combination. About 4 or 5 like that. Okay. So for all this is the design requirement to counteract the external force. Okay. But this is the actual nominal design and of the section you design, and this is the phi factor, that is 0.9, 0.85 like that. It is the resistance factor, and this is the load factor, gamma I. Here also you see that Fy is involved. It's a function. This is the maximum capacity, possible capacity of the section that relates to the yield stress. But point is this: we do not let the yield stress go up to Fy. Because why? We are dividing it by a factor of safety to reduce the effect of Fy. Similarly, we are multiplying by a resistance factor. Not only that, the gamma factor, whatever gamma, if it comes back, it is reducing this thing further. Actually, in limited design, we design the structure for a higher load. Understand? We increase the load and design according to the increased load. Consequently, the stresses developed will be less, right? So that is the meaning. Consequently, the bigger section, this side is ready for the higher moment, higher shear, higher torsion. That's the reason when the stresses develop will be less, because actually the forces coming is not that much, it is a little bit less. So that is why it is said. So that means in our case, we are designing somewhere here. If it is normally it is 1.67. If we divide by Rn by 0.67, here actually it is 0.6 Rn Fy. This is a function actually. So that means we are somewhere here or here, depending on the load conditions. But we do not use nowadays working state design. We go for the limit state design or load and resistance factor design. So it is somewhere below the proportional limit. That means we do not like the structure to exceed the yield stress. It's below that. We do not go all the way to the yield stress. This is the first condition. Second is, you know that we have another limit state. This is for the force limit state that I have discussed right now. Another limit state is your serviceability. This is the serviceability limit state. What usually we do, serviceability limit state, we do not increase the load on the right hand side of the equation. There is no factor. Even if it is there is a factor, it's a small amount. It may reduce it below 1 also, depending on it. But the function of the limit state is to see few conditions. Either it looks at the deflection, second is the vibration, and third is the cracking. So these three, deflection, excessive deflection, make the occupant or a person who is driving a car over a bridge, make him or her uncomfortable, not comfortable. Second is the vibration also make people fearful, okay? It vibrates a lot, then people get scared. So similarly, cracking, there's a crack on the structure a little bit somewhere, people get scared. So there's a limit of all this deflection, vibration, cracking, etc. All these have a limit that is specified in the code. How much it can go, how far you can travel, how can it connect, what is the limit. So that is why we always go for a smaller deflection. We do not act, because you see, I have seen in my own guys, the structure is safe for stress-wise, strength-wise it is safe, but deflection-wise it is not safe. So to satisfy the condition of deflection, we have to increase the size of the structure so that it satisfies this deflection, because we make it stiff, more stiff. So that is why the yield stress further goes down. Whatever developed stress, no, not yield stress, whatever stress developed on the structure, it further goes down than whatever we assumed for the strength design. The second, that means you have one case is your strength design, your F is lower than Fy. One condition. Second is the deflection. That means we consider small deflection. This also reduces the stress. It's further reduce this one. And third is redundancy. There's another thing is redundancy. What is redundancy? That means you use more members than the required to make the structure stable. Usually that happens. Take the case. Take the case like this. If you have a truss, you have a truss. Truss means the member, some member like this. It has a support here. It's a hinge support, a member like this. Very simple structure. It's simply supported. Assume that. This is the roller support, it can move, and this is a hinge support or pin support. It cannot move, it can rotate. And this truss, we do not take any moment. So it is the only axial forces. So what happens? This is a determinate structure. That means you can easily find out the member forces easily. I will explain what is determinate and what is indeterminate structure. Probably next class or class after that. But this is the reaction. Say it is VA, HA are the reaction, and RB, or you can say VB, vertical. This is always vertical because it is roller supported. Okay? Now, if we add some members like this, additional member, we add members like this. These members make this, they're not needed actually. But we can apply it, because what happens in a bridge, suppose it is a bridge, when you have a truck here, this member will take the load and transfer to that. Otherwise, this load will be, if this member is not there, in a bridge, truss bridge, some portion will go there, some portion will go here, and eventually the load is distributed to the members. But when you have another member like this, when the truck is there, you can take the load. But it is difficult to analyze the structure, ordinary cases. It is These members are redundant members. When you make a structure redundant, it has got less deflection because it has more member to take care of the deflection or the forces. So when a redundancy is there, you have got the less stress developing on the members. That's why your F is further lower than Fy. So that means this F, the developed stress, is always within the limit of proportionality. Small deflection case or redundancy case or strength design F is less than Fy. All these factors make the structure in the elastic range. That is the concept. Concept of elasticity is, in real cases, it is true. We have all the structure, whatever we design, all are do not exceed Fy. It is within the limit of proportionality, stress strain relation. Okay, so that is why it is called. That is because we have the concept of elasticity. That means all the structures are within the elastic limit. Okay, now there is the advantage of having them. All the analysis now on until the stress metric structural analysis or finite element analysis, always we are considering the what they call this is stress is less than strain. So stress is less than ill stress. Sorry about that. Still stress is less than ill stress, and stress is proportional to strain. Okay. Now there's another one. This is the elastic analysis, and this is very realistic assumption. Elastic analysis. There is another analysis called plastic analysis. This plastic analysis is not very much in use. It's not needed, to be honest. But it helps you, plastic analysis, how the structure will fail. That is, it give you some idea. And what happens, we allow the structure, in plastic analysis, we allow the structure to go beyond the elastic range. It goes to the plastic stage, and the moment is distributed to some other part. There also the plastic moment is developed. This way there will be hinge form, and it will form a mechanism ultimately and fail. But that is how we use elastic analysis to make the structure like a determinate structure and find out the forces or whatever it is. So this is not much relevant nowadays. It is good for analysis of portable frames. Usually it is difficult to analyze by elastic method earlier, not now, because now we have computer methods. Or the gable frame like this. Earlier they use frame like this. It is mostly used this kind of structures. Or you have some fixed beam. If you have a fixed beam, both end fixed, it is difficult to analyze. There also you can use the plastic analysis method and easily find out the forces or moments or whatever you call it. That is a different story. It's a different ball game, different way of analyzing. It is in your curriculum, in your syllabus. So I probably will discuss about the plastic analysis later. I also forgot a lot of things, believe me. We do not use it that much. So, but we will discuss about that later. But right now, we will be focusing on the elastic analysis. That is the concept of elastic analysis. The good part of elastic analysis is one very good advantage called principle of superposition. Okay? It's called principle of superposition. What is this? Suppose if you have a beam, assume a beam. You have a beam with a hinge support. This is the hinge support. It is a roller support. That means it is simply supported. Now you have a uniformly distributed load all over the beam. This is the beam. This is the beam, and this is the uniformly distributed load. Then over that you have got a trapezoidal load. And there are some concentrated load also. Suppose here one load is there, F1 or P1, you can call it P1, and the other one is somewhere here, P2. It's a complex, no? You see, 3 loads are applying, 3 or 4 loads are applying. You may be wondering why this is UDL, how it is. Say, if you have a beam like this, the self weight of the beam will be acting uniformly. It's everywhere the same. Self weight. Weight of this, if it has a section like this is self weight. And if it is carrying a slab over it, suppose a two-way slab. I will explain two-way slab. Two-way slab. Two-way slab means if you have a slab like this, roof or floor like this, if it is D is the breadth, D is the depth or whatever you call it, or you can say it otherwise. It is called B, this is called L, because this is L. This is L. So the load from this slab will be, if it is 40-degree angle, if you have a 40-degree angle there, you draw a line. You draw a line at 40-degree. This will be like this, this will be like this. So this load is a trapezoidal. See, this load will come to this beam. That is why you have trapezoidal. Two-way slab is always L over B, length divided by breadth is less than equal to 2. That means if it should be less than, the ratio between the length and breadth should be equal to less than equal to 2. Then it's a two-way slab. That means all the forces will be distributed to all 4 beams. So in that case, you have got a trapezoidal. And P is the concentrated load coming there, the point load. They're coming at a distance, say from here to here it is A, and from here to here it is B. Okay? So if you have a force like this, it's hard to find out. If somebody asks you calculate the deflection at the midpoint, delta. I will consider delta. Deflection at the midpoint. Here. It will deflect like this. So what is the deflection? This one. Or what is the maximum moment here? Or what is the value of the reactions? Because all forces are acting down. So you have only RA, reaction upward, reaction at here also upward. So somebody asks you what is the RA or RB? What is the value of deflection, delta, or what is the value of moment at this point? L over 2 at half point. Moment at L over 2 at a mid-center. You cannot easily find out. It's difficult. But what is the method of superposition or principle of superposition says that if you have a system of load acting on a structure that is equal to whatever effect of the system of force on a structure, internal forces like moment, shear, reaction, whatever the internal forces, or the deflection is equal to the summation of all those values for individual forces applied. Suppose this is equal to, this value is equal to one structure you have here, it is P1 at the space of L, A. From left hand, this is the length. The other one is so this is plus, one force is acting there, it is at B. Then third one plus, it is the same L, same beam, uniformly distributed load, I'm showing like a cloud, plus trapezoidal load. Trapezoidal load. So this plus each individual forces. If we find that the deflection here, say deflection due to the forces is a delta 1. Deflection here at the middle point because of this load here is a delta 2. Deflection here at the middle point here for this load, it is delta 3, and deflection at the midpoint is delta 4. So your delta will be now at the midpoint equal to delta 1 plus delta 2 plus delta 3 plus delta 4. That means the total deflection you can easily find out separating the forces. Okay, this type of value at the deflection at the midpoint, this load, you can easily find out from table. There's some standard table that gives you what is the reaction for a load like that. It will tell this W, whatever value will be giving, the W value, and this is also W value. Those values will be there. Okay? So deflection for that will be there in the table. This is also there. You can calculate this, replacing the values you have. Suppose it is 2 meter or 6.5 feet. You can put those values. Similarly here, all these values that will be deflection you get from the table, standard table. It has all these values. And add up, you will find out the deflection of the complex beams, complex loading system. This is called method of superposition. Similarly, these reactions will be this reaction plus this RA equal to this one plus this one plus this one plus this one. All these 4 reactions together, if you sum up, that will be your RA. Similarly, you can calculate the RB from this value. Once you have got the reactions, you can easily find out the shear force at any point. What is the shear force? Okay, when you have the reactions. Or you can find out the moment also. Moment also same. If you separately find out the moment from here or shear force here, you can add up, you will find the shear and moment there. That is the advantage of this is principle of superposition. Okay, we'll use it a lot. But anyway, and actually, to be honest, in design, in our personal case, if we have situation like this, we usually do that. We disintegrate the forces. We separate all the forces. Then find out the values from the standard table. Then add up. That is the correct value we have. This is the advantage, one big advantage of elastic analysis. And whole thing today I discussed about the concept of elastic analysis, and it's a valid analysis. Okay? It's a valid, very valid analysis, and you will use it a lot. And I will discuss more about this type of thing and elastic, all based on the elastic analysis. And today you understand what is this concept is. I thank you for attending my class. I will see you in the next class. Thank you very much. Appreciate it.